Hello. This video is about big O and how it applies in recursive functions, and we'll introduce the idea of a recurrence relation. Now we see here a standard style recursive function. This is traverse for traversing a linked list, and so as you recall, traversing a linked list is just a base case. Here it tests to see if the node being passed in is actually just a pointer to null, and if so, we have traversed the entire list, and so we just return. Otherwise, it does something. So don't know what precisely this traverse is trying to do, but it performs an action on the node itself, and then it calls traverse on node.next to move on to the next node in the linked list. So what then is the big O of a function like this? Well, what we're going to do is we're going to write down a function I'll call t of a particular size of the input, so some t of n. And first we'll look at this t function in terms of actual real numbers to see the behavior of this function. So we could say something like t of, now n, remember, is the size of the input. So if our size of the input is 0, that is we have, there are no nodes there, then we know that this value is going to be equal to the number of steps, which would be the if test and then the return, so that would be 2. So what we've done here is we've defined sort of a functional base case, a mathematical function base case. Similarly, so we're going to structure this the same way the recursive function itself is structured. And so we could say, for instance, that we could take a look at t of 1. Well, t of 1 does some work. You can see here, so if we have one node in our list, then this test fails, and so we make the recursive call. So we do the amount, so in that case we do 2 amount of work, plus then we do the recursive call. So that recursive call, recall, is actually, because the list is one smaller, because we've done node.next, is actually t of 0, so this equals 2 plus 2, or 4. So now, can we say this in a general way, define what t of n is for any n? Certainly, we just say it is 2 plus t of n minus 1. And we'll normally write this in using this notation, t of n general is equal to, and then we have a big curly bracket, and it's equal to 2 when n is equal to 0, and it is equal to 2 plus t of n minus 1 when n is greater than 0. Like that. I presume you've seen this notation before in other elements of mathematics. And this thing, when we have these two equations here, this is known as a recurrence relation. And it describes mathematically how the time grows when the size of the input grows for this function. So the next question is, how do we find out what this actually is in a non-recursive way? How do we solve the recurrence relation? And there is a 5-step process that we use, and you always just do it the same way to approach these problems, something like this. First, we write down the recurrence relation. So we've already done that. So we've got our t of n equals 2, or 2 plus t of n minus 1. Like that. So that's step 1. The next thing we do is we will expand the relation several times. So what does that mean? Well, so we take t of n, and we'll look at the more general case. That's equal to 2 plus t n minus minus 1. But we also know we can define this. We know that, do it over here, we know that t of n minus 1 is equal to 2 plus t of n minus 2. So we'll just substitute that in there and get 2 plus 2 plus t of n minus 2. And then we can do that again. If we substitute in for t of n minus 2, we get 2 plus 2 plus 2 plus t of n minus 3, and so on. The next thing we do is we figure out the ith line. Now, what does that mean? Well, hopefully you've noticed here, as we've been unrolling this, expanding out the equation, that there's a pattern here. And so if we number these lines, so this is the first line, and this is the second line, and this is the third line, what happens at the ith line? Well, what's the pattern here? This is really the key to figuring out a recurrence relation, is noticing what this pattern is going to be. And so here, we always have some sort of t minus something over on the right, and then we have some 2's that are added together, right? Well, how many 2's? Well, on the first line it was 1 2. On the second line, it was 2 2's. On the third line, it is 3 2's. So hopefully you're seeing the pattern here that on the ith line, it's going to be, I 2's. So we can write that as 2I. Right? And then it gets added to t of what? Well, look, the pattern part over here. It was always t of n, and then it was minus, and it was minus the line number. So we have t of n minus I. And that is the ith line. Next, we have to figure out the value of I that would be the base case. And in this case, so the base case here is, of course, when n is equal to 0. So what would I have to be for the argument to be 0? Well, I would have to be equal to n, because n minus n is 0. So we write down I equals n, and then we do the last step, where we take that I that we just computed and plug it back into this equation here, and we get t of n is equal to 2n plus t of, and remember that the I minus n is 0, and so that is, and that, of course, is by definition up here in our recurrence relation is equal to 2n plus 2. And that's really it. That's the process, and this is the solution to the recurrence relation. And we know that 2n plus 2 is in big O of n. So we can say that the big O of that function that we're looking at, the traverse the linked list function, is in big O of n. That's really all that we need to do, but the next couple of videos will do some examples, because you might not fully have the hang of it yet. But after we're working through a couple of examples, you'll see how it goes.